8.7, enthalpy. So this is kind of related to the rest of the chapter, but, mostly not. What is enthalpy? Well, it has to do with energy. So chemical reactions can be exothermic or endothermic. And I don't remember. Have we talked about those words before? Yes? Okay, good. That'll save a little explaining. So just brief review then. Exo is like exit. Thermic has to do with thermal energy. So this is energy leaving the system. A chemical reaction that is exothermic gives off heat. An endothermic, endo is like going in, endothermic reaction absorbs energy. The amount of thermal energy emitted or absorbed can be quantified with a function called enthalpy, which is a really funny word. And I'll just tell you right now, we're kind of lying to you here for your own good. These whole concepts of energy here are a lot more complicated than what we're going to talk about. So we're going to talk about just a very simple bit of it. And so that's what they mean by conditions of constant pressure, which is what usually happens in everyday reactions. If it's not in an enclosed vessel, it's going to be under constant pressure, the pressure of the atmosphere. But that's an important condition. So enthalpy has to do with the energy, thermal energy being emitted or absorbed. And enthalpy has the symbol capital H. I have no good explanation for that. We can think of it as heat. Okay, that's probably the simplest thing, is just to think of it as heat. And heat of reaction, RXN is the chemist abbreviation for reaction because we got tired of writing that word out so many times. And this Greek letter delta means change in, just like it did when we talked about changes in temperature. The change in enthalpy for the reaction. So we call that the enthalpy of reaction. It's the amount of thermal energy or heat that flows when a reaction occurs at constant pressure. And the energy can go out of the system or it can come into the system, but it's energy moving. So enthalpy has a sign, positive or negative, and the sign of it depends on which direction it's flowing. And so here we can think of energy like money and the reaction like your wallet. Okay? So energy flowing out of the chemical system, or we could think of that as money flowing out of your wallet. Money flowing out of your wallet. Is that a good thing or a bad thing? That's a bad thing. That's a negative experience, right? When money comes out of your wallet. Energy flowing out is negative because the system is losing energy. That's negative. Energy flowing into the system is like a deposit. So money flowing into your wallet is positive, right? It's awesome to open your wallet and find more money in there than you thought was there before. In an exothermic reaction, energy is released. In an endothermic reaction, energy is absorbed. Yeah, you said that before. Well, here's a picture. So here, the reactants are starting out with a higher amount of energy. There's different forms of energy, remember. There's potential energy. There's a lot of potential energy stored in the chemical bonds of compounds. And when those bonds are broken, that energy can be released. So what happens in an exothermic reaction, the reactants start out with higher energy, and in the process of the reaction, they release some of that energy as heat, and then the products have lower energy. So here, delta H of reaction is negative. Energy was released. The products have less energy than the reactants. In an endothermic reaction, it's the opposite. The reactants were at low energy, and energy came into the system, and now the products have higher energy. So heat of reaction, delta H of reaction, is negative for exothermic reactions. So if we look at the enthalpy of reaction for the combustion of methane, which is CH4, natural gas. So here's the balanced chemical equation, and here is a new thing over on the side. The heat of reaction is negative 802.3 kilojoules. We can look at that sign and say that's an exothermic reaction. Heat was being given off because it's all from the perspective of the system. The chemicals that we're examining here, the methane, the oxygen, the carbon dioxide, the water, those combusting there, they're giving off energy. That's a negative experience for them. Okay? The magnitude of that, the 802.3, tells us how much heat is emitted when 1 mole of methane reacts with 2 moles of oxygen. So this number is particular to the amounts specified in the equation. 1 mole of this and 2 mole of that. Okay? Because if you burn twice as much gas, do you expect to get more heat energy out? You do. You would expect to get twice as much energy, and that's the case. So when we have this delta H over here, whatever quantity that is, that's for molar quantities for this balanced chemical equation. For endothermic reactions, then, the heat of reaction is positive. When nitrogen and oxygen combine to form nitrogen monoxide, it's an endothermic reaction. It absorbs energy from the surroundings, and so here the heat of reaction is plus 182. So 182.6 kilojoules of energy are absorbed for every 1 mole of nitrogen and every 1 mole of oxygen that react. Or we could also say that this amount of energy is absorbed when 2 moles of nitrogen monoxide are produced. So this number relates to the quantities here with moles. So the amount of heat absorbed or emitted depends on the amounts. And we're going to specify that generally in combination with a balanced chemical equation. So the magnitude is for the amounts as written in moles. So I kind of said all of that already. It's as written, and it's molar amounts, okay, not individual atoms or grams or anything like that. So here is the balanced equation for propane. And LP gas is liquefied propane. So here propane reacts with oxygen to form carbon dioxide and water, and the heat of reaction is minus 2,044 kilojoules. It's a lot of energy. So that means that when 1 mole of this combines with 5 moles of that, you get 3 moles of this and 4 moles of that, and this much energy is given off. This can be used as a conversion factor. Just like we did mole ratios, we can take this negative 2,044 kilojoules and equate it to any of these guys. So we could say 1 mole of this is equivalent to 2,044 kilojoules of energy being released. So of course we're going to do that, right? Ammonia reacts with oxygen according to this equation. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So we're going to approach this as stoichiometry. So that's how it's related, even though it's like, wait, we're talking about energy now. 155 grams of ammonia. So I'm going to write that here under my balanced chemical equation. And they're asking me for how much heat. So over here under delta H, I'm going to put question mark, and the unit is specified as kilojoules. They're being kind to us. They're not asking us to convert units on top of everything else. So the path that we've learned is grams to moles to grams. So we're going to take a little detour, because what this tells us is that 906 kilojoules of energy are released for every 4 moles of that formed. So I'm going to just write that in here. So minus 906, and the minus just tells us what direction. It's like if you're balancing the books, keeping track in your checking account. A minus means that it went out, a plus means that it came in. That's all it is. That is equivalent to 4 moles of ammonia. So if we want to get to kilojoules, we need to get to moles of ammonia. We're given grams of ammonia. So what we're going to do in our path here is we're going to go grams to moles, and we're going to take a little detour here to kilojoules. We don't have to do the rest of it. So 155 grams of ammonia times, and we're going to go to moles of ammonia, and then we're going to go to kilojoules of energy. And the units, we're going to follow our pattern with dimensional analysis. So that our units all work out. So as I wrote up here, this heat of reaction is giving us the relationship between this amount of energy and these molar amounts of reactants and products. We don't need to go moles of one thing to moles of another thing because the energy relates directly to any of them that we're interested in. So that's where we got the 4 moles of ammonia and negative 906 kilojoules. There's a negative sign in there. It's okay. Your calculator will understand. This guy right here is a molar mass, right? So we need to calculate that. 14.01 plus 3 times 1.008, and that's going to be 17.034. Grams of ammonia per mole, or grams equals 1 mole. 17.034 down here and a 1 there. So we got 155 divided by 17.034 times negative 906. Make sure you use the change sign button and not the minus sign. Divided by 4. Well, I divided by 1. That doesn't do much good. Divided by 4. And my calculator is showing me minus 2061 point a whole bunch of stuff. And the unit there will be kilojoules. So if we're going to pay attention to sig figs, we're going to keep 3. And we'll end up with minus 2.06 times 10 to the 3 kilojoules. Now, you can't have negative mass, you can't have negative number of objects, but you can have negative energy. Because the heat is flowing, it's moving. It's really almost impossible to measure heat statically as a quantity. Just heat is flow of energy, and so it's going one way or another, and that's all the minus sign tells us is what direction it's going. Any questions? This part, this idea of interpreting the equation is not new. What's new is we're throwing this energy term in here. Here's another example. So what mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat, and what mass of carbon dioxide is produced? So they're asking us for two different things. What do you notice that's weird about this equation?
Fraction.
It's got fraction in it. I thought we couldn't do that. Well, it's not ideal, okay? It's not the best, but this is balanced, okay? And what's important is that this number, this heat of reaction, applies to the equation as written. So with the fraction in there. Don't go clear the fraction without messing with this. I mean, if you really can't stand that fraction and you multiply everything by 2, you also have to multiply this by 2. We don't really need to do that, though. So here we've got an amount of heat, and we're asked for mass of butane. So let's see here. We've got 1.5 times 10 to the third kilojoules. Now, it's telling us that in words, produce that amount of heat. Is that amount of heat negative or positive? Is it being given off or taken in by this reaction? It's being given off. So really, that has a minus sign. And the question is, what mass of butane? So how many grams of this? So this is similar to the previous question, but we're going to work backwards. So our path is going to be kilojoules to moles to grams. Because this negative 2,658 kilojoules, that's how much energy is produced when 4 moles of this is burned. So that is a relationship that we end up using as a conversion factor. So we'll start with minus 1.5 times 10 to the third kilojoules. And we're going to go to moles of butane. That was propane. So C4H10. And then we're going to go to grams of butane. Keep forgetting which gas we're dealing with. Wow. I'm just going to start that one completely over. Grams. C4. Finish the H. 10. Grief. And then we put the units in so they cancel out. Lost my ability to write and talk at the same time. Same pattern we've been following. The twist is that we're throwing this kilojoule thing in there. Okay, the relationship between kilojoules and moles comes from this number and the number of moles specified in the equation. So 4 moles of butane and minus 2658 kilojoules. And then we've got grams of butane and to moles. So molar mass there, 4 times 12.01 plus 10 times 1.008. It's going to be a long day. Four times 12.01 plus 10 times 1.008, 58.12. So 58.12 grams of butane are equal to 1 mole. So now we have 1.5 times 10 to the third, it's a negative number, times 4, divided by another negative number, times 58.12. That just doesn't look right to me. I think I did something wrong. Oh yeah, I did. I did negative third instead of... so that's 1,500 times 4 divided by 2,658 times 58.12. That's better. How many sig figs should this have? 2. So I'm getting this, so I'm going to round that to 1.3 times 10 to the 2 grams of butane. Yes, question?
Can you go over how you knew 1.5 times 10 to the third was negative?
Yes. How did I know that the 1.5 times 10 to the third was negative? So what mass of butane is necessary to produce this amount of heat? The key word is produce. So I'm gonna clear this out of here for a minute.
We could just look at the negative 2,658 kilojoules.
Cause yeah. There's a couple of different ways to think about this. So when we look at this heat of reaction, we see that it's negative. That tells us this is an exothermic reaction. It's giving off energy. So if we're asking what mass of butane to produce this amount of heat, is the heat being given off or is it being taken in? Well, it must be being given off. And so therefore it's also a negative. Now, I am teaching you the proper use of the negative and positive signs on the energy. For the purposes of this class, I think you can mostly get along with just ignoring them. So if you put down positive 1.5, what's going to happen in your calculation here? You're going to end up with a negative mass, right? If that was positive, then you're going to end up with a negative mass. Can you have a negative mass? No. And really the only thing that went wrong there is you didn't pay attention to the sign. And so then you say, well, gosh, that's impossible. It must be positive, and you'll be okay. So you can fudge a little bit on that. Does that answer your question?
Yeah.
Any other questions?
So absorbed would be the opposite.
Absorbed would be the opposite. And when another way to write these, you can write an exothermic reaction like that, showing heat as a product. And if it's an endothermic reaction, heat is a reactant. That doesn't give you anything about the sign, though. There you really have to think about the sign. The sign is positive if it's a reactant, and negative if it's a product. Question?
Is the final answer one negative one?
No, it's positive. The red is if you did it incorrectly. If you didn't take into account the it came back. I don't know what that was about. But they're the negatives are gone. So the correct answer is 1.3 times 10 to the 2.
For the mass of butane
for the mass of butane. But there's another question, isn't there? How would we calculate the mass of carbon dioxide? We could either do this same thing with carbon dioxide, or you could take this number and do regular stoichiometry and go from this mass of butane to moles of butane to moles of carbon dioxide to mass of carbon dioxide. But let's do it the energy way. So if I want to find out how much carbon dioxide is produced when 1.5 times 10 to the third kilojoules of heat is given off, again, I'm starting with that minus 1.5 times 10 to the third kilojoules. But now I'm going to go to moles of CO2. So how many moles of CO2? What's the coefficient? It's 4, right? 4 moles of CO2 produce this amount of energy. 4 moles of CO2 produce negative 2658 kilojoules. The kilojoules cancel out. And then here, I need the molar mass of CO2. So that's 2 times the mass of oxygen plus the mass of carbon. So we've got, let me do the math without talking. $99 grams of CO2. So I'll do it the other way up on top here. Let's clear that guy out. So I could also do it by starting with the mass of butane that I just calculated, grams of C4H10, grams to moles, to moles, to grams. Filling in the units. So the molar mass of butane we already did, so I'm just going to copy that down from the previous equation. In the mole ratio here, we've got a 4 in front of butane and a 4 in front of carbon dioxide. So those both end up being 4. And then we need the molar mass of CO2. And the answer there comes out with 2 sig figs to 98 grams of CO2. Is that a big problem? No. It's not a big problem. Where is the difference? It's in the last digit, the 9 and the 8 here. That is the uncertain digit. Why is it off? Because I used the rounded number. I'm going to punch it through again using the whole number that we had gotten, 131.196 divided by 58.12 times 4 divided by 4 times 44.01. And now I get 99. So that's an example of a rounding issue. And on the exam, on multiple choice questions, if you came up with 98, there's not going to be 98 and 99 as the answer trying to trick you, okay? And so you say, well, yeah, the difference is in the last digit. That's the uncertain digit. It's probably just a little rounding issue, and so you choose the 99. Any questions? I'm hoping this is the end. Here's a word of advice about the homework. Yeah, so Q. Q is heat, and they just suddenly are springing Q on you. What you need to understand from this little thing here is that in the homework, a lot of times they're asking for the absolute value. So they're saying in the homework, ignore the sign, ignore the negative sign. Just tell us the amount. And then they use words to convey whether the heat is absorbed or given off. If I'm going to say that this amount of heat is given off, then I don't need the negative sign, because the given off tells us that. So this is something to be, everyday chemistry, Bunsen burners. So this is just kind of practical for in lab. When you have a Bunsen burner flame that looks like a candle and is giving off a lot of light, it's also going to give off a fair amount of smoke. And this means that it's not getting enough oxygen. Here, there's no oxygen being mixed with the gas that's coming up. It's just burning with the oxygen that's available around it. As we add more air, the flame gets bluer and hotter. And this is ideal. And if we go to too much air, we start to see this floating flame. And then you're going to have a flame that's going to blow out easily. So if you light your burner and it keeps going out, cut back on the air. Okay? Not enough air is bad, and too much air is also bad. So there's chapter in review.